Okay. Yeah. Then I'll have to go there. Pick somebody will change it. I tell you, take it. Hmm? Yeah. I will. Okay. The hand will be. I give it. Thank you. Good morning. I would like to thank Principal Nancy and Professor Sun for inviting me to give this talk. Agency, agency, topic is instrumentation control for Indian PHWR is nuclear power plants. PHWR is pressurized water reactor. Now, we use instrumentation control in almost all the process industries. So, how it is different when you do for the nuclear power generating plants? See, nuclear plants are associated with the presence of radioactivity, and when you design a system, it has to ensure that the radioactivity doesn't get released to the atmosphere because this radioactivity harmful to the living things. And if it goes in phases, it may cause severe damage from minor damage of hair loss to changes of genes or sudden death also. So whenever we design any system, we need to ensure that the system never fails in a way which will lead to the release of radioactivity to the atmosphere or to the water bodies. Now, before I don't know how many of you know about the nuclear reactors. So briefly, I will tell you what is a nuclear reactor. Nuclear reactor uses fuel like uranium or plutonium and as a neutron source. When the neutron from the neutron source is absorbed by the fuel atom, it becomes unstable and breaks into some and breaks into two lighter atoms called fission atoms. See what happens when the neutron interacts with uranium plutonium. The number of neutron will increase. There is a ratio of neutron and proton. If goes beyond certain limit, it becomes unstable. That is how when a single neutron goes to uranium, it becomes unstable and it breaks into two lighter. There is some problem it is changing also. Is there cable connection? So it breaks, and the breaking is not like that you have got a piece of coal and hammer it and breaks. It breaks into two different atoms. So two new atoms are two lighter atoms get generated, which are called the fission products. The breaking of few atoms is called fission. And if you take the sum of the two fission products, it is less than the original mass of uranium. Because when the fission occurs, two or three more neutrons get generated. The sum of mass of the two fission products is less than the mass of electron. This is because fission products also associated with the liberation of two or three neutrons. This loss of mass gets converted to energy by the famous relation T is equal to mc square. M is the change in the mass and c is the velocity of light. This energy is in the form of kinetic energy of the fission products. Once the fission reaction has been started in few atoms by means of an external source of neutron, fission can be maintained in other unit atom by the neutron produced in the previous phase. In every fission, two or three neutrons are generated. So even if one or two neutrons gets absorbed in the fission reaction of the other next unit, this will continue. That is what called a continuous chain reaction. In a fission reactor of uranium-235 atom, around 200 million electron volt energy is generated in the form of kinetic energy of the fission. This means if all the atoms contained in 1 gram of U-235 undergo fission in one day, we can generate 1 megawatt power. Thus, 1 kg of uranium-235 can produce energy equivalent of 2,800 tons of coal. The kinetic energy of fission turbines gets converted to heat energy when it is absorbed by the material, and then this heat is taken up by the water and gets converted to steam, which drives the steam turbine and you alternator connector. So if you see, you must have read about the thermal power plant in which you use coal or oil to heat the water in the boiler, and that is used to convert it to steam, which drives the steam turbine. Then connected to alternator, is connected to your transformer, you connect to the transmission line. Everything is same except how heat is generated. There is generated by burning the coal or oil. Here you do by fission. Okay. So this difference shows there is uranium neutron comes to fission products and two or three neutrons get generated. These are the fuel bundles which is used in the reactor. 19 fuel element bundle used in 220 megawatt. The last one is 37 fuel bundle which is used in 700 megawatt. If you see the fuel bundle, there are some wires you can see which are the special wires create a gap through which the water can flow, and then inlets through support this together. This shows another picture in which this is the uranium oxide metal. Uranium metal is not used because uranium metal is fine. Around 600 degrees it changes the phase, so its volume increases and break the cladding. So they use uranium oxide metal which can go to high temperature. And the fuel bundle supported in the inside the pressure tube, which again support as the current here. And the material used is zirconi because we have to make sure that water neutrons get generated do not get absorbed. And this zirconi has got left probability of absorbing neutrons. This is another photo of fuel bundle inside a pressure tube and outside is a conveyor tube. The pressure tube is supported by a tube through what is called a garter spring. It is a spring from this is another photo. This is what you see a reactor vessel which is around 6 meter long and 6 meter diameter. And there are around 306 channels in 230 megawatt and 392 channels in the 700 megawatt. This is another movie. This photo. This was some better connected to connect large number of pressure tubes inside the fuel bundle. In the bottom there is coolant water goes to this. So this is basically exactly exactly same as the thermal power, except that this portion is different. Here you see the current. Yeah, these are the fuel bundle one. Water goes through this, gets, and this is heavy water goes through this, gets converted to goes to extended data, and here this line of infrared water comes, it gets converted to steam and the steam turbine. And this is water, sea water, which condenses the steam here in the condenser. Water goes back. So this is closed. So there are three systems. First is the coolant, is the heavy water coolant here. This is devalued water. And this is your sea water. At present, we are having around 24 reactors generating 8,780 megawatt. 9 reactors are under construction, and 8 reactors are planned. So by around 32 or 33, we are going to have 41 reactors with 21,880 megawatt. This is the list of the reactors at various places. Now, in India, we have got 4 types of reactors. One is called boiling water reactor. This is the first reactor supplied by General Electric long back in 1969 at Tarapur. The fuel is enriched uranium. Now, what is uranium? Uranium, natural uranium has got only 0.7% of uranium-235, which goes under those, and 99.3% is uranium-238. Uranium-238 is not fissile, but it is fertile. If absorbed the neutron, then it gets converted into plutonium, which is again fissile. So in PHWR we have enriched uranium. Enriched uranium means by process you increase the percentage of uranium-235 in the fuel, and it is not primary coolant is water, and there is no secondary coolant directly C1. So what happens? Primary coolant goes as a stream also, and there are chances of radioactivity going. So nowadays no one uses boiling water reactors. Most of the Western countries use pressurized water reactor, in which you use enriched uranium. Primary coolant is water, secondary coolant water. Enriched uranium is percentage around 2 to 4%, and India, we started with pressurized heavy water reactor, which uses natural uranium. The reason was because we did not have technology that time to enrich the uranium. Neither industry was able to make a large pressure vessels needed for the PWR. So we had to go for the PHWR with natural uranium, and heavy water is a moderator and coolant, and the secondary are water sea water. So, but now today we have got technology for enriching the uranium to any extent up to 100%. Also, we have industries able to support us with the pressure vessels, and this PWR is actually compact. They don't use moderator. What is moderator? Moderator is water surrounding the current inside the current vessel, which reduces the energy of the neutron. The neutron which gets generated in the fission reaction have energy of 2 to 10 mega MeV, whereas for U-235 fission we need only 0.025. So these energy gets is reduced by scattering process in the water. But water has got a more absorption for neutron as compared to the water. And now we have used PWR for our submarine project because those are the compact reactors. So there we have used uranium. And last one is the fast repeater reactor, which has first reactor has come in Kalpakam, which has become critical and will be operations. Now let us come to our actual topic. After we have learned a little bit of reactors. So instrumental control system for forming protection, control, or related tasks in the nuclear power plant responds all elements from plant systems to control actuators and includes provisions which facilitate operation, research, testing, online diagnostics, maintenance. So, like any other process industry, whatever is your sort sensor to sense the current process parameters, voltage, pressure, and then you compare that method with the set point, find out the error, to create the algorithm, then give it to actuator which can be a control. So same, everything is like that. But here we have to make sure that it is highly reliable. When INC system perform functions important to safety, these systems must be demonstrated to be safe and reliable with accurate data. See, if I have designed a system and I say meeting all performance requirements or functional requirements, and I should be able to, I am not allowed to do it. Because it has to be seen and approved by what is called atomic energy. That's what a set of experts, which will go with each and every design aspect. I have to make, one has to make a large number of documents which of the experts committee approve, and once they approve, then only it can be reactor. So in nuclear power plant, we have three types of systems, distributed control system, called IA, IB, IC. IA is a protection system, IB control system, and IC important for plant operation but not directly affecting nuclear. Now what control system does? Control system does that it maintains the parameter within certain safe limits, within the design limits, by controlling its process. And the protection, if some parameter goes beyond certain limit, then it may cause some fault or failure. So, protection system has to make sure the parameter, if the control system fails, parameters are brought within them. Either the power is reduced by step back or set back, so that parameters comes within limit, or if it is not happening, then what we reactor has to be shut down. And for that, what we do, we have got shut off rods which are hanging above the reactor. It is hanging with rope by magnetic clutch. If anything happens, a shutdown reactor signal goes and the magnetic clutch is de-energized and the rods will fall because of gravity inside. So that, because what happens in any reactor, how do you control power? Finally, it's controlling the number of neutrons. More is the neutron, more fission will have, power will increase. And when the number of neutrons reduce, power will increase. So what will happen is what is called a react. What is K effect? That is the how many number of neutrons get generated in present reaction to the ratio of the previous fission cycle. So if more neutrons get generated, power will increase. So that is how you control, by controlling the control rods, which are the neutron absorbing rods. So if you remove the neutron absorbing rods, neutron will increase, so power will increase. When you put it back, power will reduce. Somewhere when they we have to move the control rod so that it remains same and power is maintained. So that is how you control. Similarly, when you shut off rod falls, it is neutral material. It will absorb and bring down the power. That is one protection system. Second thing is the worst condition in the accident in the case of reactors is loss of coolant. If suppose the pipeline breaks and or water, cooling water is not available, then core may melt and it may lead on water. So what happens for that purpose? Will water is stored in the big tanks, 25 tons or so, and that water will continue. And it will really do where all water will go to in the reactor building some, and the some pump will start, certain pump will start, it will continue to set water. Lot of water may be evaporated and there may be pressure inside the building. So building is designed in such a way, which is called a containment building, that given that pressure, no radioactivity can leak outside. Even the porous, we see the leakage of the building, that the porous of the cement and concrete that don't allow the things to go. And above that there is second containment. So in Indian PHWR type of things, the chances of releasing the radioactivity because of prevent the core meltdown is almost because you have shut primary rods. In addition, there is second condition of liquid poison. Gadolinium nitrate is kind of water. So it's fully shut down. Even if suppose there is a break of some other breaking like loss of coolant incident, then liquid is contained building and there is second containment. So at the highest, this is a protection system. And the control system has to maintain the parameters in safety. But control system should also be made highly level. It should not unnecessarily ask action by the protection system. It should on its own should be able to. Because what happens when protection system was shut down, you are bringing power from let's say 1000 megawatt to 6%, that may be 60 megawatt in no time within 1 or 2 seconds. And there will be a lot of thermal shocks. So the mechanical structure gets. So control system has to be highly reliable and should not unnecessarily ask for the action of protection system. So first layer is we follow what is called defensive philosophy. So first layer is the control system, as I told you, maintains plant parameters in set limits, prevent operational runs due to accident condition, and minimize the need for extraction of protection. Second is reactor setback or reactor step back. That is, the parameters goes beyond this by reduce the power by step back or setback. And third layer is the protection system, which I already told, shut down reactor, remove heat from the core. See, even when you shut down, immediately power gets used to 6%. So you have to 1000 megawatt reactor, now 60 megawatt, which itself is a big reduction. So shutdown rate has to, the shutdown pumps continue for 2 to 3 days, unless to remove the heat and control accident conditions. Now, you might have heard about the Fukushima accident. Actually, in other reactors, there are what facilities, there is earthquake immediate shutdown takes place. So in Fukushima, when this earthquake occurred, it immediately shut down, and the shutdown cooling pump started. But that earthquake was around 2 kilometers below the sea, and it was because of the vertical movement of the plates. So water was thrown up, and tsunami was there. For that purpose also they had put a wall of around 12 meters height to take care of tsunami. But this time tsunami was beyond 12 meters. And water came inside, and all the shutdown from electric things was covered with water. and thus even shutdown cooling could not start, which led to the so whenever an accident happens anywhere in the world, also intergovernmental agency, and then to all the members, and every country has to make sure that this type of accidents don't occur in there. After Fukushima, our shutdown codes in all the reactors were taken to higher levels so that emissions from what occurs get. And especially in Tamil Nadu, where last time tsunami had come, there also we have made 10-meter high walls that if tsunami will not. Now, what are the design requirements of factory critical control system? Mandate parameter which is safety. Okay. High reliability, safety, security, and availability. High reliability. How do you ensure high reliability? How do you ensure high availability? Availability is what? You know, mean time between failure MTBF, and there is something called MTTR, mean time to repair. If mean time to between failure is high and mean time to repair is low, availability is MTBF minus MTTR divided by MTBF. So you have to ensure that your MTBF is very high, MTTR is very low, so the availability is high. And how you do high reliability? There are various ways. One is using the redundant system. Now in nuclear power plant, we use triplicated system. Although one system can do the job of controlling, but we will have triplicated system. We will have stores, we will have three sensors going to three different systems, and they will generate output. The output for analog systems, what we will have a median selection. All the three outputs will go and find the median. Median means suppose output 9 million. Right, the middle median. And for the all the distal outputs, use 2 out of 3. So this redundancy is what then using good components. Many things are required to be manufacturing. You provide cooling, you provide proper wires, because when you are giving signal, but then it noise gets become. So you have to use extra shielded cables to avoid the electromagnetic interference, and the shield has to be grounded to avoid the electrostatic errors. All those things you have to take care of. Minimization of error by avoiding complex design. Design has to be as simple as possible so that you are not likely to make errors. Fail safe output. Now, this is one of the things fail safe output, which is very much. If your system fails, still reactor has to be in safe condition. And as I told you about the shuttle system, which is connected to drum and held there by clutch. If power supply fails, what happens? Clutch will be energized. So if power supply fails, it goes shut down. So it's safe condition. Similarly, say suppose I am controlling certain pressure of primary coolant pressure, which is around 56 kg per centimeter square. 56. So I can, it is controlled by there is some input or output fall in the system, and we manage that thing so that pressure is maintained. Now if system fails, we can keep the wall as it is in the last condition. So our system is designed in that way. Okay, like it will fully close up, it will remain in that condition. You have to design it. High MTBF is assumed by design redundancy. Design with adequate margin on critical design. So wherever, say suppose you are using some relay output for connecting to something, it has got a 2 ampere rating. You make sure that you are going to connect more than 1 ampere. So wherever it possible, you provide the redundancies and this. For example, power supply. If my system needs 5 volt 10 ampere, I will provide, I will not operate at 10 ampere. I use 5 volt 10 ampere to power supplies connected through shortly diode to the load. So that each supply will be 5 ampere. Even if one power supply fails, other is fail. But this is one system. There are 3 systems. Each system has got 2 power supplies, and they are also connected to 3 different sources, 3 different UPS. So suppose first is there are 3 UPS A, B, C. The first system will be connected to A and B, second B and C, third is C and D. So that even if 1 or 2 UPS fails, 1 or 2 power supplies fail, the system is available. Design of power supply with adequate availability. Physical separation provides common cost. Even if I have duplicate the systems, I don't keep all the 3 systems in one room. They are kept in separate rooms with fire barriers. 3 sensors are there. The cable from the sensors to these systems are routed to different paths. So the fire at one area doesn't affect. And then they are connected. And also fire, the cable used are FRLs. Fire retarded to other now we continue with design requirements. There is a low empty here, mean time to repair. As I told. So we design the system in which you should be able to remove the faulty board even online. So it has to be pluggable type, first thing. Since you have to have pluggable, if you remove any pluggable things, it is likely to fail. So what we do, the power and ground pins are longer than the signal pin. So when we put the board, power and ground gets connected first before the signal gets connected. And when we remove, signal gets disconnected first. So this will not cause failure of the boards. You can do online. You should have enough spare. But more important is which board has to be. Has to be. How will you know that? So what is the online diagnosis? So we in our control systems we don't use commercial board. All hardware boards are designed with FSLER online diagnosis. Now what is online diagnosis? For example, if it is ADC, then you must see that ADC is working properly. So for that you have a zero input as well as a fixed reference IC you have to use and see that it remains linear. For digital input, we use what is called finite impulse testing (FIT). Through software, temporarily we bring the input testing and see whether it is really changing or not. That's called finite impulse testing. Which is done during diagnostic cycle. For analog output, which is normally 4 to 20 milliampere, we feed back to the one of the channels of the ADC, all the outputs. One separate ports is used for that purpose. And see what we have output is really right. If it's not there, we know the port is not there. So this online diagnostic becomes very important to achieve low NPTR and hence high availability. Online diagnostics and fault tolerance I have explained. Layout to permit easy maintenance so that any board can be removed anytime. Protection against virus. We don't use any, it is an embedded system. Software, it is an EEPROM covered with the black. So there are no chances fire entry. There is an information system, PC based information system, but there also is a traffic is only for information one way, that is to inform the current. Isolation system network on the plant network. Plant network is different and the system network remains isolated. display of parameters to indicate the status of the equipment and system, that is any other system regarding a single parameter for post-event analysis. These are all common things. Multi-level access to previous. Now, other requirements must be demonstrated to be safe and reliable with appropriate area performance. Now here, to achieve that, you have to make sure that your hardware is highly reliable, your software is reliable. Hardware is easy because you know the failure rates of the components. So what we do, we have hardware and there are n number of components in that. Any single component value is taken as a failure of the code. We find out failure rate of all, calculate the reliability of that. And since they are triplicated board and all other boards, we make a fault tree and find out the overall system reliability. It can be done. But how to find out the reliability of software? There is no way to find out the reliability of software. So what we do is, I will come to that. How we do with software. And safety analysis system design. Hardware and software. What is system analysis? There are a large number of hardware components, software components. We consider each component. If this fails, what will happen? What will be its effect? Power supply fails, what will happen? Okay, because we have to make single failure criteria. If out of 3 systems, 2 systems fails, of course this is what protection system is good. But single failure, so if power supply fails, what will happen? Whether it is separated, what will happen? Whether it will go to safe state. So for all hardware things and software things, we do that, make a proper document, see like what will happen. If it happens, it has to be in a safe direction. Now comes the important, safe and high integrity software. Complete, dependable, free-form defense. How this is ensured is done by well-defined systematic software engineering process. Complete design documentation, version control, detailed skill was review, concurrent verification, and validation by so, now suppose somebody wants to set up a plant and he says, I want this plant, you want to control pressure, level, temperature, whatever, some processes. He will first a document will be made which is called a system requirement, what he wants to achieve in any industry. Then based on that, a concept document is made which says how I am going to achieve the requirements. What part I will do software, what part I will do in hardware, with process. All those things will be done, and then it is checked with respect to system requirement that it is met. After that, we make what is called hardware requirement document, software requirement. What processor I will use, what should be the ADC resolution, what should be the how many inputs are there, how they are connected. All those things will come. In software, which is important, we have to make a software requirement specification. And software requirement specification has to be dependable, unambiguous, and complete. Each requirement of system should get reflected in software requirement, and there should not be any extra. And it has to be unambiguous. I will give an example. Because everything is written in English. And somebody has written a software requirement application. I will give an example in Hindi. It says, Gaadi roko mat jane. Stop the vehicle, don't allow it. Now something like that, if it is ever written, the person who reads, he can read, Gaadi roko mat jane. Stop the vehicle, don't allow it. And then he can read, Gaadi roko mat jane. Don't stop the vehicle. So, it is ambiguous. Now, if same ambiguity is there in your software requirement specification, you will design it for that. And finally, when you supply, you will find it is not working. And one, you must know that software modification is much more costly. Because afterwards you find out, you will redo the job, lot of money is involved, lot of time is involved, and more than that, during patchwork you may introduce some more error. So right from beginning, you have to make sure that software requirement selection is complete, unambiguous, and dependent. And each requirement we make a matrix that is requirement of software requirement, system requirement, measure with this thing, 1 to 1, and nothing is extra, and this measures. So that matrix, after software requirement specification is made, then software design document is prepared, that how I am going to achieve this. The ideal term, what integration will I follow, how I will do. All those things have to be written. And then there is what is called concurrent verification. Verification is a process done by independent team of people who will check each and everything matching with the previous document. Like software design is matching with the software requirement, software requirement matching with the system requirement, coding is matching with the software requirement. They go to the code work. So all these things is done very systematically. That is called the verification process, just to avoid it. And the verification is when the software is developed and integrated along with the prototype system. Then you test for various inputs what is the expected output you are generating out. So what is the difference between verification and verification? Verification is a black box because you have certain only limited number of inputs for which you see the output. Whereas with the verification software, you can try various combinations. You can see whether it will fail in any way. That is why software following a systematic operating procedure becomes very important. Now I will take a test technique of 12% of system. As I told you earlier, systems we were using replicator system, but I myself designed one configuration called 12% of system, which I have used in 520 megawatt nuclear power plant for controlling certain processes like primary coolant pressure, pressure, forget about process, but I will tell you about the configuration. So this was installed in 2005 in Tata 4, 3 and 4, 540 megawatt vehicles. And I have to tell till today there is no problem in this system. What is your PHWR? PHWR, there are two systems. There is called system 1 and the system 2. System 1 and system 2 are identical. It has got two microcomputers, 1A and 1B. This is not microcomputer 2A. So I will explain one only. So microcomputer 1, there is a process with evaluation circuit to connect this microcomputer to the and they got all analog inputs which can be processed signal across 100 get point input to point forward. And they got dedicated analog input port in this system. So really, first microcomputer 1A will read it all the inputs and generate the output and will put its output in dual port mode. After that, microcomputer 1A will also read all the inputs for the calculate its output and generate and write in a dual port. Now, microcomputer 1A will compare its output with the microcomputer 1B, and 1B will also compare with its. If any of this microcomputer finds that outputs are not matching or two cycles, then it is taken as a there is some problem with the part and it is declared. So what happens? Output of, let's say there are 20 outputs, 1 to 10 outputs will go to one control transfer unit and 11 to 20 will go here. Similarly, 1 to 10 of this, the identical unit will come here and 10 to 20 will come. This is actually a relay type of thing. Normally this is get connected to the output. And here And here it is connected here. So 11 to 20 is normally going here, and 1 to 10 is going here. 20 outputs are there. So normally, if this is working properly, both are working properly, outputs 1 to 10 are controlled by this to control oscillator. And 1150 by the second system. If somehow microcomputer variant 1 they find that their outputs are not matching, then this walnut time arm will cause the control transformer to change, and this will get connection will get changed to this. So now all the 1 to 10 and 11 to 20 outputs will control by this system. So if this fails, this takes over. If this fails, it's the hardest to buy because both are working continuously. And this is the actual system which was manufactured in electronic workshop and get interpreted under testing at the time. So you see this is the processor code image. Both are there representation here. This is bus master. Here it is and bus here it is. So bus gets extended is a digital input output port with analog input output port. There is signal conditioning port which provides the transfer isolation for inputs. This is number. So performance, reliability, safety, and availability requirement is made by the right fault-tolerant computer architecture as I explained. Using in-house developed microcomputer hardware with facility for online diagnostics. Redundancy, DC power supply, AC power connections I have explained. Input and output isolation for both analog and digital signals. Transfer isolation and mark isolation for digital. Fail-safe outputs. Related and independent plant. These are already software is developed under software quality assurance plan. Programs run under in-house development. We don't use the operating system. We have all real-time multitasking. Online diagnostic promptly detects any fault in the control system and gives diagnostic messages. So that software development cycle includes software requirement execution, software requirement execution, software design, integrated testing. At this stage of cycle, appropriate document is generated and is subjected to independent review by the team. The structural modular design approach is followed. That means software that enables dependent check out. Software verification where techniques are used to ensure I already explained. Integrated software modules as well as integrated system software and hardware tested on the prototype system for functional performance requirement. Test of integrated system ensures compliance with functional requirements. So in conclusion, in Indian nuclear power plants, the practice of design and implementation of computer-based systems for gaining of functions important to safety has matured, and it is impossible to demonstrate that with this model. Thank you. Anything related with the nuclear plant or reactor, I try to answer.
Sir, in general, the power production and different ways, it is one of the ways to get a maximum power compared to other power generation stations, like a thermal as well as the water hydropower like that. I think the Indian government has not given a lot of importance to the nuclear power plants compared to the
Government.
Indian government has not given full importance for this nuclear power plant compared to the other power plants because Other power plants they were established, like in the NTP, I mean, NTPC, yeah, like that. Why they were not giving so much importance to this nuclear power plants?
Nuclear. Okay. Thank you. Nuclear plant, the nuclear technology says that nobody, no country will share it. You have to develop for your everything. If you know, the first go contest happened in 1970. After that, there were a lot of restrictions of after BAE getting any item from the national countries. Everything we have to develop. Right from at that time when our industry was not mature, power supply we were not mature. Everything we have to develop right from the beginning. So that way it was helpful to us because it helped made us research field and we were able to make plants. As I told earlier, so that 1974, Rajasthan 1 and 2 reactors were made and we were getting help from Canada. The day 18th May 1974 happened, next day everybody left. And the Indian scientists were really in problem because now they have to work on their own. It took 10 years to make our operation. But after that, so many reactors. Now, as far as you are saying support from the government, government has declared by 2047 we must have 100 gigawatt of nuclear. And if you see already, I have shown the list by around 32, 33, we will have around 21 gigawatt. And it is possible to achieve. The thing is, the operating cost of nuclear plant is less. Initial capital cost is more. But initially, everything was being controlled by only government agencies. That is only Department of Atomic Energy because of its way nuclear reactors work. But now government has opened it to private industry and many industries like Tata and they have L&T and others, they are entering into this field and they are
Privatization of nuclear power plant is there.
Huh?
Privatization of nuclear power plant is there.
Yeah. So, but then they are mostly importing and then putting here with incorporation. Main thing is India has got a limited number of limited amount of uranium available. We have one mine in Jadugona, Bihar, but recently we found out in Andhra Pradesh, Sublapalli. But it can sustain, I think, not more than 10,000 megawatt for long term. Kudankulam project, which is we are taking from Russia, they have assured a lifetime fuel supply. So that is it, and that is what we will. Larger is coming from outside because fuel is important. We do have quantity around 30% of the world. But thorium is not size. It is volatile. It gets converted by U233, which is uranium-238. So that's why we have got a three-stage program. The first program is PHWR, in which we use the natural uranium, which is only 0.7% U235. And uranium-238 gets converted to plutonium. So that plutonium is a and it is also used in nuclear weapons. Then plutonium, along with the U238, because we don't have much of these things, it is not, we reprocess the used fuel, take out the U238 and then plutonium by chemical processes. In other countries, they just use once and then store it. They are not bothered because they want enough. But we have to do that. And let this U238 will be is being used in orbital reactor, in which plutonium will generate the power, and U238 will get converted So more fuel will be generated. And also we will have some blanket of 232 sodium, which will get converted. So we have to now have second phase. We will have to make a large number of phosphate reactors to get 233. And once we get enough 233, we will go to third stage where we use 233 as a fuel and sodium as a blanket. So you burn it 233, more U233 gets generated by converting sodium to. So it will happen, but it, every stage take time. Even second stage we will have to work for around 30 years to get the enough U230. And government is now producing. Sales like only 100 gigas of plants. Any other questions? Really safe. Already. Done. Safety, these special safety features is asking. Features, measures you have taken. Safety, okay. Say in India PHWR, safety is assured when some failure happens. We have to make sure that the radioactivity doesn't get released to the public, to the atmosphere or water bodies. And for that purpose, we have got what is called a protection system. Protection system to shut down by dropping the shutdown rocks. Second protection is cooling has to be continued, so we have got some storage tanks of rainwater which will provide cooling. And even if suppose your coolant tubes get ruptured, the water will fall to a reactor building in a sump, which is again continued. And then both is contained in a reactor called containment, which is designed to sustain even the water gets evaporated, pressure gets up. And we see even the leakage of the buildings so that it doesn't go out. And apart from this first containment, we have got the second containment. So chances of radioactivity going to the atmosphere, and I can tell you till today in India there is no radioactive release in India. And radioactivity is also much less as compared to the natural radioactivity finding. If you go to let's say Tirupati or you go to Kerala, it's 0.4, 0.4 to 0.7 millisieverts. Whereas in India, it's much less than that. Even if you go in sun, you get radioactivity. If you fly plane, you get more doses than. So, actually, the body has got a mechanism that reduces also. So, you should not get a full large dose at one time. Small dose, which you get, it
What kind of sensors are used for?
I'm not.
Types of sensors. Types of sensors used in the.
What kind of sensor is used for measuring that neutrons?
There, neutrons, what is called is we use ionization chambers sort of things when a neutron, and in some places we use a fission counter type of thing. For example, with fast breeder reactor, we have a detector which is coated with uranium, and the neutron generates a fish. Neutrons, which interacts with certain gas, and gas is ionized, and then you provide potential, see the current of the ionized gas molecule, and then find out what is this. So you have to calibrate it with this. So this is called a fission counter. Similarly, you got an ionization chamber for thermal power plants.
Are these also manufactured in India?
Yes. Fission counter, which I told you, which is in FD, that has to operate at 450 degrees centigrade, and that was the first time made in India. That no better neutron reactor working at that temperature also. Because normally in thermal reactor PHWR, we keep ionized chamber outside where temperature is 60 70 degrees. But here when they design, it is kept inside the reactor. So temperature is high there. So it's just to sustain a lot of time because it is not only my part was the instrumental study. But uh, coating on the material, coating of uranium to 35 on material itself was a difficult process for the fuel division. It was real challenge, but we could do that. And we could get good sensitivity because now we have got 100% certificate available. We do have now capability of reaching uranium and all the everything is now what you call cradle to grave. That is right from fuel manufacture to design, operation, everything, even the processing of food is indigenous and can be done. Thank you.
Any questions?
Hello, sir. I basically wanted to ask why was PHWR chosen as a better nuclear reactor in comparison to PPR and FWR? Like, why does India maybe lead with this specific nuclear reactor and why not the other options? Like, why did it start out with that?
Say, as I told you, PHWR uses natural uranium. And when we started in India, we did not have technology to use to increase the uranium. Enriching means that you are increasing the percentage due to 35 in the natural uranium is only 0.7%. So when we did not have technology, we did not have because nobody gives you the fuel, especially in this fuel. Second thing was the industry was also not ready to make the large pressure vessels which is needed for this purpose for the PWR, which other countries use. Other countries have their industry support for making pressure vessel and they had facility for industry. So they were doing. We had to do this thing. So in our case, we have used pressure vessels, pressure tubes, which are only 3.25 diameter, and which we could make at our nuclear fuel complex in Hyderabad, which is made of zirconite. So we had to go for PHWR. PHWR, the another thing is there that since number of it is uranium available in the 0.7%, we have to economize the neutrons because only 2 or 3 neutrons gets generated in each fissure. If they get lost in a non-fission reaction and get absorbed in some material, then it becomes a problem. So we have to use moderator which slows down neutron and at low energy there is more probability of going. So we use today we can enrich uranium to uranium to 99.99%. There is industries which is available in pressure vessel, and that is why and since PWR technology doesn't use a separate moderator, the light water itself acts as moderator because it is increased uranium more uranium fuel is available, so you need not have to economize, so you don't need a moderator. So it is compact, and that is why in our nuclear submarines we have used PWR technology. There it is enriched uranium with water. So what was told that Rekhat and Daman which we have worked on that and we've done the control system for complete nuclear. That is based on PWR. Thank you.
Hello, sir. Since you are from an electrical engineering background and we are also electrical communication students, how much of your current profession is actually relevant to your engineering?
See, this question is asked by many, that what we are studying, how much it is useful in our future career. See, control system was of course covered in electrical engineering, but I will tell you one thing. In 2008 and 9, 2008, I was asked to go to Indore at one, where we got one unit, which is called a Rajaramana Center for Advanced Technology. There we have got an electron accelerator, in which the electron accelerated to the almost to the velocity of light and it rotates in the circle. The current is 100 milliampere. Now you know the electron charge is 1.602 minus 19. You calculate 100 milliampere will be how many billions of electrons have to, and it has to flow continuously. And this was a field which was not, I had never worked, but I was asked to go. What was happening? It was working for 1 hour, half an hour, then will stop. Because current will get lost, it will get absorbed. So I was asked to go. I told this is a directive field, I don't know ABC of the things. How I will do? The director of that unit said, I have confidence. So I had to go study. It is not that your study ends with your belief. Study continues till you, even today, at my age is 75, still I have to. So study never asked to do, I do it and try to find out. There were many problems. I will tell you very simple. I studied, you must have read the history system. Is it not? In electronics. Now what was happening, every day they will start and they will take just 2-3 hours to stabilize the current. And it was, every day it was different level of parameters which they have to set. The problem was, when you switch off, there is something called retentivity. You know, when the distance comes coming up at 0, there is some magnetism. Next day you start from there or somewhere else. So I said, why do you do that? Let us, before starting, take the current from the source, electron source. You recycle the magnets 3 times. And then what? And within no time they will, whatever they will expect for work. Similarly, when I studied electrical engineering, they were taught tubes, even transistors were known. Diode, electrode, etc. But if I have to be in time, I have to study microcomputers, I have to make the systems without never read ADC, DSC or anything. I have to do that. If I have to be real. So the study never ends. And it should never end. If you have to be successful, you have to continue to study throughout your life and be relevant. You are seeing today, everybody is doing software and doing IoT coding. In our time, few years back, there was craze. I will also read HTC, I will read Java, I will do this and go into the software. Today, it is taking over. So, to be relevant, you have to learn. So, like that, study never. And one thing is there, which you are reading, you are studying today, These are basics which is already there in your mind. And even if you take new things, all this well indirectly helps you. You will not. See, there was one project which is a secret type of project which I was involved related with the nuclear doctrine. Nuclear doctrine says we will not take any country with nuclear weapons unless we are attacked. But if we are attacked, we will cause unacceptable damage to the environment. This is the but how to implement it? Its implementation is very because if somebody, everybody knows your adversary is in China or Pakistan, everybody knows your adversary. So they will not leave you with one problem. If they have to draw, they will draw you all number of bombs and make you so that you are not able to conquer. So you have to be ready for it. And if suppose this do a normal bomb and you think it was a big bomb and it will be the bomb and you try to do it, whole international this thing people will be against you. So first thing is within 10 minutes you must know if there is a nuclear attack. Nuclear attack it has to go to the center where counter attack can be done. But they will not where they will attack. They will not attack your only military installation. They will attack your command center. They know who is the command prime minister. After that, national security advisor or someone. There is a chain of who can, if one is not available, who can give command. They will try to destroy them. So you have to protect them also. And protect in a way that they can stay in a safe place inside some bunker. I will not tell more than that because it will at some place where even an atomic bomb is dropped nearby by radioactivity, by pressure, by so and from there communication system should be available to give command, go ahead. Communication system cannot be on there. There has to be low frequency, high frequency, very high frequency, your antenna based on that. Sometimes your antenna base will not work because if it is atmosphere, that will get charged because of the atomic bomb. So all these things, and then you have to protect your electronics because when atom bomb drops, what is called electromagnetic pulse gets generated, which is destroyed all the electrons. So you have to protect your. So these all things come indirectly by what you study, how to achieve that. And you have done this. So for that, only your basic knowledge which you are studying now comes to you. But to be relevant in this in your career to progress, you need to be always up to date. I hope I have answered it.
Thank you, sir, for your valuable insights into electronics and instrumentation. Your role in placing safety have truly motivated all of us. We are truly wanting to learn. We are genuinely mean it from our body. And we are also sorry for the inconvenience happened.
That's great.
As we come towards the conclusion of this event, it is time to express our gratitude to everyone who has contributed to making this event possible. I now invite Dr. T. Sridhar sir to deliver the vote of thanks.
Very good afternoon to one and all. Sir, it is highly appreciated for giving your valuable time to us. In spite of several works, we have spent around 2 to 2.5 hours with our around some 200 students in this initiative after the retirement. We are truly honored as a resource person to our students. So the first and foremost, respected Padma Shri Chandrakant Pitwar sir, distinguished scientist and pharma director, E&I Group of Mumbai, and our beloved professor and the principal of the CPIT, CP Nasim sir, of the department, Dr. K. Vasu, and also as the convener of this program, and the respected faculty members, student coordinators, and the participants. On the behalf of the Department of Electronics and Communication Engineering, Chaitanya Institute of Technology, and IIT of CBIT, I extend my sincere gratitude to everyone to present for making this effort to make this event as a grand success. Before I begin, I would like to share a motto of our second body of our IIT, that is Vidya Bharati Vinaya. Knowledge gives the humility. So whatever the information that is shared in this today's session related to the nuclear power plant, and it is almost is a new topic for us. Around from 5 to 6 years onwards, we have not listened such kind of a new topic, and it is a well-known word to us, but we have not known about in detail about the nuclear power plants information. It was an immense honor to have a Padma Shri Chandrakant Pitwar sir with us today. Thank you for sharing your valuable insights and instrumentation control for Indian PHWR based nuclear power generating plants with focus on design, performance, reliability, and safety aspects. I also thank our principal sir for his continuous support, Ramana sir for giving and suggesting you as a resource person for this section, and also the other department, Dr. K. Vasan sir for organizing the event, and also the other faculty coordinators of our event, Dr. K. Vasan, Dr. B. Madam, Dr. K. Sridhar, and Dr. K. Sakshi. A special thanks to our student coordinators, Rajat Mishra and K. Kartikeya, and other IIT faculty coordinators and the CPC members from the CBIT. And finally, thank you all to the participants for your enthusiastic presence of staying around 2 to 3 years. And also, I sincerely please excuse because of the schedule of the students having the lunch in between these two durations, and the student bus has to leave. Maybe there may be a notice about the here and there some movement. Please excuse us from the organizing side. So, we are grateful to you, sir, and we hope we will listen few more lectures from your side, sir, in future. Thank you, sir. Thank you.
I request all the dignitaries.
I think I delayed your lunch. Sorry.
No problem. Can you join us for a group photo?
I request all the dignitaries, students, and student coordinators.
Students, everybody. Come. Students, come.
Requested to come to the desk for the group photos. Please come, please come.
Come, Randy. Please come.
Students from maybe India.
Ma, Randy.
Requested to come to the desk for the group photos. Please come.